Welcome to Talk Tensors, your deep dive into machine learning research. Today, we're really getting into something fundamental for autonomous agents, robustness.
Yeah, how do we make sure they actually work when they leave the lab?
Exactly. You train these things in perfect conditions, but then the real world throws a curveball, maybe different lighting, a weird reflection.
And suddenly, performance just tanks. We see it with drones, self-driving tech concepts, even game-playing AI sometimes. It's a huge hurdle.
It really is. We need agents that can, handle that ambiguity, that fuzziness of reality.
Which is why this paper we're discussing today is so interesting. It's called Robust Decision-Making via Free Energy Minimization.
Right, and the core idea feels different. They've got this model, DR-FRE, that's DR-FRE, and instead of just hoping robustness, emerges from tons and tons of training data.
Which is kind of the standard approach, right? More data, hope for the best.
Exactly. DR-FRE tries to build robustness directly into the agent's decision-making, using this free energy minimization principle.
It's trying to install it by design, not just by accident.
That feels like a smarter way to go. So our mission today is to really get under the hood of DR-FRE. How does it pull this off?
Yeah, we'll look at the mechanism, put it in context with the whole free energy idea in AI, and think about where this could lead.
Okay, so let's start with the overview. DR-FRE, you mentioned it's a free energy model, but what's the DR part, the extra sauce?
So it has this distributionally robust extension, that's the DR, and it works alongside something they call a resolution engine.
Distributionally robust.
Right.
Resolution engine.
Okay. And basically the combination lets the agent make decisions that aren't just, optimal according to its training model, but also resilient if that model isn't quite right.
How does it do that resilience part?
By aiming to minimize the free energy in the worst case scenario across a whole set of possible environments it thinks might exist.
Okay. So it's like, what's the worst this could be within reason, and how do I best handle that?
Precisely. And that's a big deal because, as we said, many current AI systems are brittle. They're amazing in their training box.
But you change one little thing,
and they fall apart. Think game AI confused by a minor graphics update, or a robot arm struggling if the lighting changes slightly. Natural intelligence, your brain, my brain, we handle that stuff much better, often without needing specific training for every tiny variation.
Yeah, we generalize, we adapt. So the key contribution here is tackling that brittleness head on, designing for robustness.
Exactly. It's a different philosophy. Not just hoping for robustness through scale, but engineering it into the decision logic.
Which could have huge implications, right? Thinking about multi-agent systems, robots in unpredictable places.
Definitely. And maybe even giving us clues about how biological systems manage to operate so effectively with sometimes very limited data or training in really complex worlds.
Okay, you keep mentioning free energy minimization. It sounds important. Let's rewind a bit. Where does this idea come from? What's the history here?
Right, so free energy minimization isn't new. And it's not just an AI thing. It's actually this concept that pops up in information theory, machine learning, neuroscience, even cognitive science.
Wow, okay. So a unifying idea.
Some propose it as exactly that. The basic postulate is that adaptive systems, organisms, maybe even some AI, behave in ways that minimize this quantity called variational free energy.
And what does that mean, minimizing free energy?
Think of it like trying to minimize surprise. The system has an internal model, its expectations about the world, and it tries to act in ways that make its sensory experiences match those expectations as closely as possible. It's constantly trying to improve its predictions about what's going on.
Okay, like reducing the error between what it expects and what it sees.
That's a good way to put it.
Yeah.
So traditionally, an AI using this principle would have a single model of the environment, maybe learn from its training data.
Got it. One model, learned from experience.
And it would choose actions to minimize free energy based only on that one model. It assumes the model is correct.
Which is where the problems start if the real world doesn't quite match the model.
Exactly. And that's the jump DR-FRE makes. It says, okay, we have this trained model, but let's not assume it's perfect.
So what does it do instead?
It considers an ambiguity set, basically a collection of possible environments that are statistically close to the trained model.
How does it define close?
It uses a mathematical measure called Kohlbach-Lybler divergence, or KL divergence. It quantifies how different one probability distribution is from another. So DR-FRE defines this sort of neighborhood of plausible realities around its main learned model.
So it's not just one map. It's like, here's my main map, but reality might be slightly warped in these ways.
Exactly. And then the core robust principle kicks in. Choose the action policy that minimizes the maximum possible free energy across all the environments in that ambiguity set.
Okay, minimize the worst case free energy. That sounds fundamentally more cautious.
It is. It builds in a buffer against being wrong about the environment.
So computationally, how is this achieved? You mentioned two components earlier.
Right. First, there's the principle itself, the distributionally robust free energy, FRE idea of considering the ambiguity set. Second, there's the resolution engine.
And the resolution engine is the part that actually finds the best action.
Yeah, it's the algorithm, the machinery. It basically works in two stages. First, figure out the potential cost of the ambiguity by finding the maximum free energy within that set. What's the worst it could be?
Finding the peak of the mountain, so to speak.
Kinda, yeah. Then, knowing that potential worst-case cost, it finds the policy that minimizes the free energy, taking that worst case into account.
So find the worst possible scenario within your uncertainty, then find the best action for that worst case.
That's the essence of it. It leads to policies selected under a best-worst case logic. It's like the AI is hedging its bets against its own model being slightly off.
Okay, that makes sense. So DR-FRE explicitly accepts that the training model isn't perfect, that there will be these training environment ambiguities.
Yes, it's designed specifically to be robust against those inevitable mismatches.
And the amount of mismatch it considers is tunable. You mentioned quantifying uncertainty.
Exactly. That ambiguity set we talked about, defined by the KL divergence. Its size is controlled by a parameter, the radius of ambiguity, often denoted AIK.
ITE.
Radius of ambiguity.
A small radius means the agent is pretty confident in its trained model, so it only considers environments very similar to it. A large radius means low confidence, so it considers a wider range of possibilities.
So you can dial up or down the agent's level of caution, essentially.
Precisely. It reflects how much uncertainty the agent needs to account for. Mathematically, this whole thing fits into a sequential policy optimization framework. It gets a bit technical, but it involves nonlinear costs and probability distributions over actions.
And the output, the thing DR-FRE actually gives the agent.
It gives an optimal policy the best strategy for acting that is specifically robust to that chosen level of ambiguity. And, crucially, it also tells you the best performance you can theoretically achieve given that ambiguity. That's really interesting, not just the how, but also the how well is possible. So it sets expectations based on the uncertainty.
Yes, it establishes performance limits.
The paper also mentions some, cognitive implications, things we can learn about intelligence itself from this.
Yeah, a few things stand out. One is that the resulting DR-FRE policy is often interpretable. You can kind of see why it's choosing certain actions because of the ambiguity.
That's good. Black boxes are always a worry.
And it naturally supports Bayesian belief updating. The agent can update its understanding as it gets new information, which is fundamental for learning.
Makes sense. What else?
Well, it formally shows something intuitive. An agent facing ambiguity cannot do better than an agent that knows the environment perfectly. Uncertainty always hurts performance, essentially.
No free lunch.
Right. But conversely, as ambiguity shrinks towards zero, the DR-FRE policy smoothly becomes the same as the optimal policy for an agent with perfect knowledge. It connects back nicely.
Okay, that's reassuring consistency.
And maybe the most intriguing part. When ambiguity gets really high, the optimal policy starts depending less on the specific training data and more on the agent's prior beliefs, its built-in assumptions, and just how large that ambiguity radius is.
So when you're really lost, you fall back on your basic instincts or priors.
Kind of like that, yeah. It suggests a potential mechanism for how systems might operate when faced with completely novel situations where their specific training is irrelevant. It really makes you think about the interplay between learning and innate biases.
That is fascinating. It feels like it connects to human intuition somehow.
It potentially does. And the researchers didn't just leave it at theory, they tested it with real robots.
Ah, right. The Robotarium experiments. Tell us about that setup.
Okay, so they used these small, real rovers in a controlled lab environment called the Robotarium. The task was pretty standard. Get to a goal location, avoid crashing into obstacles.
Simple enough. Where did the ambiguity come in?
They intentionally gave the robots a flawed model to start with. The model they used for planning was learned from biased data, so it didn't perfectly represent the actual layout and physics of the Robotarium.
So the robot's map of the world was deliberately wrong.
Slightly, yes. Enough to cause problems. And the results were pretty stark.
What happened?
The standard agents, the ones using traditional free energy minimization without the DR-FRE robustness, they mostly failed. They'd crash into obstacles because they were acting based on their faulty map.
Makes sense. If your map is wrong, you navigate poorly.
But the rovers, equipped with DR-FRE, they consistently succeeded. They managed to navigate around the obstacles and reach the goal, even though they were working with the same flawed initial model.
Wow. So DR-FRE allowed them to overcome the bad map.
Effectively, yes. Its inherent robustness allowed it to compensate for the mismatch between its model and reality.
Yeah.
And they showed this not just in simulation, but with the actual hardware moving around.
That's a strong proof of concept. Seeing it work physically really drives the point home.
It really does. It underlines how damaging even seemingly small ambiguities can be for standard agents, and it shows DR-FRE providing a practical solution.
Okay, the paper also gets into some novel notions stemming from DR-FRE, hinting at where this could go next. What were some of those?
Well, one interesting insight is how ambiguity shapes the policy. DR-FRE tends to make the agent assign lower probabilities to actions or states that are associated with higher ambiguity.
So it learns to be wary of the uncertain parts of its plan.
Essentially, yes. It becomes more risk-averse about the things it's unsure of. It prefers paths or actions where the outcomes seem more predictable according to its potentially flawed model, plus the ambiguity consideration.
That sounds like a sensible survival strategy. What about extreme uncertainty?
Right, so in cases of really high ambiguity, the model shows something fascinating. The agent's decisions can become dominated not by the learned model details, but by its prior beliefs, from its underlying generative model and the size of the ambiguity radius itself.
So the training data gets ignored if things are just too uncertain.
To a large extent, yes. In some experiments they mentioned, with very high ambiguity around obstacles, the robot might actually ignore the obstacle avoidance part, because that's where the ambiguity was high, and just head straight for the goal, which was the point of lowest ambiguity in their setup, even if it meant crashing.
Whoa. So extreme uncertainty makes it revert to its most basic goal, ignoring learned constraints.
That's what the framework suggests could happen. It raises really deep questions about how agents should balance exploration, exploitation, and safety when facing radical uncertainty.
Definitely. And on the flip side, low ambiguity.
As we touched on, when ambiguity is low, the equiradius approaches zero. The DR-FRE policy neatly converges back to the standard optimal policy you'd get without considering ambiguity. So it behaves correctly in the easy cases too.
Good, it doesn't break things when they're simple.
And importantly, the framework proves that ambiguity always makes performance worse compared to having perfect information. There's always a cost to uncertainty.
Right, no ambiguity premium. One other thing mentioned was belief updating, being able to infer costs.
Yes, this was another neat extension. Because the policy links actions to costs and ambiguity, you can potentially work backward. If you observe an agent acting, sequences of states and actions, you can use the DR-FRE framework to estimate the underlying cost function and the level of ambiguity that likely drove those actions.
So you can figure out what the agent was trying to achieve and how uncertain it felt, like inverse reinforcement learning, but with ambiguity built in.
Kind of, yeah. They actually did this in the experiments. They observed a DR-FRE robot, then used this Bayesian life updating method to reconstruct its cost function.
And did it work?
Apparently, very well. The reconstructed cost function closely matched the actual cost function they had designed for the navigation task. And robots using this reconstructed cost with DR-FRE could also successfully complete the task.
That's impressive. It suggests you could learn an agent's goals just by watching it, even when it's acting cautiously due to uncertainty.
Exactly. And they compared it briefly to a standard maximum entropy inverse reinforcement learning technique, which apparently struggled to converge to a good cost estimate in this ambiguous scenario. The DR-FRE approach offers a potentially more stable, convex optimization problem for this kind of cost reconstruction.
Okay, this has been a really thorough look at DR-FRE. Let's try to pull it all together. What's the big picture significance here for machine learning?
I think the big picture is that DR-FRE offers the first, or is one of the very first, computational models based on free energy principles that directly tackles environmental ambiguity to achieve both optimal and robust decision-making. It addresses that core brittleness problem we started with.
So a major step towards agents that can handle the real world's messiness.
Potentially, yes. It provides a principled way to do it.
And for listeners trying to stay on top of ML research, what are the main takeaways?
I'd say a few things. First, robustness doesn't have to be just a lucky byproduct of massive training. You can actually design for it. Second, DR-FRE gives us a formal way to think about the role ambiguity plays in decisions. Third, it helps understand the limits of performance when dealing with uncertainty. And fourth, it opens up possibilities for things like interpretable policies and better belief updating.
So it's really a framework for thinking about and dealing with uncertainty in AI decision-making, a shift from just assuming the model is right.
Exactly. Acknowledging the uncertainty and planning accordingly.
Okay, well, that gives us a lot to think about. And maybe here's a final thought for everyone listening. We've talked about DR-FRE, balancing priors, learned models, and ambiguity in AI agents. Could these underlying principles, this interplay between belief, experience, and uncertainty, maybe give us a new way to look at decision-making in other complex systems? Not just AI, but perhaps biological systems too. Think about how organisms navigate constantly changing environments with limited information. Are they, in some sense, implicitly doing a kind of robust, free energy minimization?
The fascinating question. Could this connect information theory, robotics, biology, cognitive science, even more deeply?
Something to mull over. Definitely food for thought at that intersection. Thanks for joining us on Talk Tensors for this deep dive.
Glad to be here.
We'll catch you next time with more from the frontiers of machine learning research.